All right, so the recording is on. The other day we were in Chapter 2, working our way through Chapter 2, which is the chemistry lecture. We'll do some of this in lab as well, so there'll be a nice repeat, and that's the good thing about the lecture material and the lab material, the way we set it up. You see the stuff in lecture, and then we talk about it in lab, so it kind of really helps you reinforce. But what I want to talk about today, what I want to begin with, is talking about why atoms go through this process of making bonds. Now, you know, the why, I'm just basically going to put out there the reason why atoms engage in the bonds that we're going to discuss, and there's three basic types of bonds that we're going to be talking about. Three basic types of bonds that are important for, that occur in chemistry and important for living organisms. But the reason why atoms do this is basically, as I mentioned in class, stability. It increases the stability of the system when these atoms engage in these types of bondings that we're going to discuss. Now, if you take a chemistry class, you'll get a little more detail about, you know, and mathematically can calculate how that stability increases. But we don't need to be really too worried about that here in a biology class. We just need to know the types of bonds, you know, what's going on in these bonds. And again, the why behind that is really nothing more than just increasing the stability. Everything out there in the universe, all these atoms, all these chemical compounds, it's all about reaching an equilibrium, reaching a stability, and that's why everything is happening the way it was. That's why the universe is expanding. That's why entropy increases. We talked about entropy as one of the characteristics of life. Entropy is the amount of disorganization. So the opposite of entropy is something that's organized. Now, Mother Nature, as a whole, doesn't like things organized. She likes things more disorganized. And what I mean by that is she likes things spread out. That's why the universe, as I said, is expanding. That's why all the planets and the suns and the stars eventually through time will disintegrate. And what will happen is it'll make this uniform collection of material throughout the universe. So you, as a collection of materials in one spot, you kind of represent an organized part of the universe. And Mother Nature is trying to disorganize the universe. She's trying to make it even throughout. She's trying to make what we call a homogeneous mixture, a homogeneous collection of all of the matter that's in the universe. Hello, folks. I got an email from one of your fellow classmates. Let me answer this back. 1 second, folks. All right, here we go. Okay, so that's basically what I mean by the fact that as far as the increasing of the stability. When things, and we'll talk a little more about this in subsequent chapters when we get to energy and that sort of stuff, but things basically are more stable when they're separate, when they've fallen apart. They're less stable when they're put together. And that's why we never can defeat entropy. And that's why you can never live forever. And that's why nothing can ever last forever, because actually we represent sort of an unstable state. And things are falling apart because they're trying to reach stability, all right? So I don't know if that's a great explanation as to why atoms engage in these bonds. If you take a chemistry class, you get a much better explanation. But like I said before, we're not going to worry too much about the concepts behind that. More, we're going to focus on what types of bonds are formed and what the results are. So the first type of bond that I want to discuss with you folks is a bond known as a covalent bond. And oftentimes in science, if we look at a word, we can sometimes break up the roots of the word and get at least an approximation of the definition. So, for example, the other day when we were discussing homeostasis. Homeostasis, if you break up the words, homeo means same, okay, and stasis is state of being. You know, so what basically homeostasis means is same state or same state of being, and that's what I'm talking about with the teeter-totter thing, with the seesaw. Everything in a balance is in homeostasis. It's in the same state. So you get a little bit too warm and you sweat, like we talked about. You get cold and you shiver, right? All those sorts of things. So if you look at the word covalent, we can do the same thing with that. For example, the root co CO. What's that mean? When we see that in other words, what's that imply? And if you're trying to think, what are the words? Think about co-chairman, co-captain, Coca-Cola. Well, maybe not Coca-Cola. Yeah, with or sharing, right? Like the co-captain in an airplane would share the duties. That's supposed to be captain, not caption. But that would share the duties with the captain. The co-chairman chairman shares the duties. So we got here CO is sharing. What are we sharing? Well, valent, and you saw that word before. Let me see. We go back a couple slides and remind you. Right. One more, I think. Oh, one more. One more. There we go. Valent, right? Valent refers to electrons. Remember, we said the outermost shell of an atom, the outermost shell is known as the valence shell. And in the valence shell, there are electrons. Now, sometimes in the case of neon, there's a full outer shell, because remember we said that we're having 8 electrons fills that outer shell, because that outer shell has 4 orbitals. Now, again, I want to emphasize to you folks that a shell does not physically exist. If we could see atoms, and maybe someday we'll actually get to that point, we are more or less getting better at being able to get images of atoms. But if we could ever look at them, we would never see a shell. We would never see electrons in neon zipping around, all 8 of them, in this one circular type of arrangement you see there. You remember in class we said that shells are actually made up of orbitals. And the orbitals can have a variety of shapes. They can be shaped round. They can also be shaped in a dumbbell shaped. And so that's the physical structure where the electrons are found. So the electrons in the 1s orbital are found somewhere in this sphere. Now this is, of course, we live in a 3-dimensional world. And in the 2s orbital, there's 2 electrons in that sphere as well. And then the p orbitals, each of those can hold a maximum of 2 electrons as well. So when we say that the outermost shell, like in neon, or the second shell, is full when it has 8 electrons, what we're doing is we're saying there's 2 in the S-shaped orbital, and then there's 6 in those P-shaped orbitals, and 2 in the S, and 6 in the P-shaped, makes a total of 8 electrons. Okay? So this part in the lower left, this S orbital, and these 3 P orbitals that I'm indicating, all collectively together make up the second shell. So you see what I mean when I say that shells don't exist? Shells are an artificial creation of human beings. The physical property or the physical structure in which electrons are found in are called orbitals, right? That's where they are. All right, so let's go back to our covalent bonds again. So what we're doing in covalent bonds is we're going to be sharing a pair of valence electrons. Now, when you see the word valence electrons, I want you to think valence is talking about the electrons in the outer shells. Atoms engage in chemical bonding for the most part with electrons in their outer shells. And the reason, and I mentioned this in class the other day, and the reason why they're doing that is because it increases their stability to have full outer shells. Not all atoms as they are have full outer shells. Neon just happens to. And if you may have remembered from some of your earlier chemistry classes, neon is a noble, N-O-B-L-E, or an inert element. It's a noble or an inert gas. And what we mean by that is neon does not react with anything. And the reason why it doesn't react with anything is because it's stable. It's got 8 electrons in its outer shell. It's not missing any electrons. It doesn't have a shell with only 1 electron like we talked about that chlorine or that sodium did. So that outer shell, that valence shell, is full. But if you don't have an outer shell, if you don't have a valence shell that's full, then the electrons in that outer shell are going to engage with electrons from other atoms, and when they do, it's going to form a bond. So if you look at the picture here, let's look at the hydrogen atoms. Hydrogen has the atomic number 1. All right, and as I've mentioned in class, oftentimes we don't put the atomic number, but if we did, the atomic number would be that number in the lower left-hand side. But that's not just numbered based on, some arbitrary idea of, hydrogen's 1 and helium is 2. That means something. That means something physical about that atom. Hydrogen has the atomic number 1 because it's got 1 proton. And since things are in balance in life, that means that hydrogen also has one electron. Now, hydrogen is also unique in the sense that it doesn't have any neutrons. The other elements have neutrons. But we don't concern ourselves when we're talking about bonding and discussing the nucleus. The protons, like you see in the picture, the red one, and the neutrons, if there were any, they're in the nucleus. The bonding occurs between the electrons that are out there in those shells. All right, so hydrogen has the atomic number 1. That means it's got one electron in its one and only orbital, which makes up its one and only shell. All right, now let's do a little review. How many electrons does it take to fill an orbital? In other words, what's the maximum number of electrons you can put? Hold on a second. Orbital, not shell. Orbitals. How many electrons does it take to fill that orbital? There you go. And that orbital. How many electrons does it take to fill each one of those p orbitals? It's all 2, right? You can only put 2 electrons in an orbital. So if hydrogen only has 1 electron, that means it only has that first shell. And in that first shell, remember that's the artificial part, there's an actual physical structure known as an orbital, a 1s orbital. The s refers to the fact of the shape of the orbital. S orbitals are round or spherical shaped, and p orbitals are those dumbbell shaped ones. So if hydrogen only has 1 electron in its one and only orbital, that means that it's not stable, right? Hydrogen gas very easily explodes. It's not inert. It does react. That's what an explosion of hydrogen gas is. It's a reaction. So 2 hydrogen atoms in the universe coming close to one another, each has the same dilemma. Each one only has 1 electron in its outer shell, and that's not stable. So they would like to have 2 electrons in their outer shell. So let's say hydrogen atom number 1 says to hydrogen atom number 2, hey, let me have your electron. Let me have your electron so I can have 2 electrons in my outer shell, and I can be stable. Now that's good for hydrogen atom number 1, it's supposed to be 2 I's, but it's not so good for hydrogen atom number 2. Because once hydrogen atom number 2 were to lose that electron, then it's no longer even an atom. It's just a proton, it's a subatomic particle. Now later on in the semester we're going to talk that does happen, but in the context we're discussing today, it does not. We're not going to give up an electron. Instead of giving an electron from one hydrogen atom to the other, what they're going to do is, you see in the picture to the left, they're going to share the electron. See? They're sharing those electrons. So hydrogen atom from the left and the hydrogen atom from the right, each one contributes 1 electron. Each one now has 2 electrons in its outer shells. And those electrons, as I mentioned, always like to travel around in pairs. So when we share things in a covalent bond, in some cases we're sharing those electrons equally. And what I mean by that is the electrons, as a pair, are going to zip around the nucleus of this hydrogen atom about 50% of the time, and they're going to be found about 50% of the time around this nucleus of the atom. If you added it up, if you watched H2, which is 2 hydrogen atoms stuck together, and you looked at the electrons, about half the time the electrons are around the one on the left, and about half the time they're around the electrons on the right. So they share, or the atom on the right. So they're sharing those electrons. And when you're sharing those electrons, you make a bond. Now we indicate covalent bonds, a little bit of chemistry shorthand here, with a line. See that line between those 2 H's? The H is the atomic symbol for hydrogen. The line represents a sharing of 1 pair of electrons. And we write that formula out as H2. Notice the numbers on the right-hand side, not on the left. Right? Again, the number on the left is the atomic number. The number on the right, if there is a number, is how many atoms you've got. And just as a review, remember up here would be the atomic mass. All right? So we got 2 hydrogen atoms sharing a pair of electrons. That increases their stability, and that makes what we call a single covalent bond. It's a single covalent bond because you're only sharing 1 pair of electrons. Now there are other that get together and share more than 1 pair. For example, 2 oxygen atoms. Now oxygen has the atomic number 8. Okay, atomic number 8. So let's run through the drill here. How many electrons are there in the first shell of oxygen? In the first shell. Right. It's always going to be 2 in the first shell, folks, because there's only 1 orbital in that first shell. How many electrons are in the second shell of oxygen? Right, exactly. So that means that oxygen is missing a pair of electrons. Y'all are telling me 6, and we've discussed already and established the fact that you need 8 in that outer shell to be stable. So 2 oxygen atoms come together, and what they're going to do is they're going to share not 1 pair of electrons, but 2 pairs of electrons, which is what we call a double bond. And double bonds are indicated by not 1 line, but 2 lines. So anytime in chemistry you see 2 atoms written out with a line between them, that line specifically tells you the type of bond that's occurring, which is covalent, and the number of lines tells you how many electrons are being shared. You see in the picture there, the oxygen are sharing 2 pairs of electrons, or 4. Now, if you count them out, 2 in the first shell, and again, just like the hydrogen, those electrons are going to be spending half their time around the atom on the right and half the time around their atom on the left. And so we got 2, 4, 6, 8 in the outer shells. All right, that's a double bond. We can go one step further. Certain elements, for example, like nitrogen, can actually create not double, but triple bonds. In this case, we're sharing 6 electrons, 3 pairs of them. And that's known as a triple bond, which we indicate with 3 lines. Now, I know some of you have had chemistry, so maybe you've discussed this, but I think that sometimes when we look at things, it seems intuitively obvious. First of all, let me get rid of my scribble. But between those 3 bonds, the single that we see in hydrogen, the double in oxygen, and the triple that we see in nitrogen, which one would you hypothesize, using an educated guess, is probably the stronger bond between those 3? Triple bond, right? The triple bond, because we're sharing 3 pairs of electrons, right? And those pairs of electrons being shared, that's what forms the bond. The sharing of electrons is to complete the outer shells, to increase the stability of those atoms. But since you have to share them, then you're going to form a bond. You see, the thing is, if you're missing an electron in your outer shell, if you need an extra electron, or in some cases, if you have an outer shell that only has 1 electron, you can't just release that electron into the environment. Likewise, if you need an electron, there isn't a pool, like that card game Go Fish, there isn't a pool of electrons you can draw from. There's no rogue electrons running out there. Any electrons out there in the universe are spoken for, if that makes sense. They're already attached to an atom. So that's why when the 2 hydrogen atoms got together in the first regard, the one was unwilling to give up its electron, right? The electrons are not just something that if you need one, just take one from a pile. If you need one, you have to engage in a reaction with another atom to get that electron, or in the case of oxygen, to get that 2 electrons, or nitrogen 3 electrons, 3 pairs, right? So keep that in mind as we go through our discussions of how electrons are important for biology, that if you need an electron, you have extra electrons, you can't just get rid of that extra electron and say, okay, good, now I'm stable, and you can't just pick up some rogue wandering electron and increase your stability. They have to come from somewhere. Okay, does that make sense? So here's some other pictures of other atoms that are sharing electrons. There's the hydrogen and the oxygen. The Lewis dot structure formula there, the little dots you see between, that's just another way to show a covalent bond. It's a little more because it's indicating, what electrons are being shared and how many are not being shared. Like in oxygen, obviously we see the 2 pairs in the middle are being shared, and then the oxygen has its other 2 electrons as well. Don't worry so much about that Lewis dot structure. That's something that it's actually probably better saved for a chemistry class. The lines, though, I would like you to know that when there is a line drawn between them, it specifically is referring to a covalent bond, and it's specifically referring the number of lines to the number of electrons. All right, so let's look down here at water, very common substance, right? Water, there's an oxygen being attached or bonded to 2 hydrogens. Now, in this case, we're fulfilling the outer shells of each of those atoms, but in a little slightly different way. A hydrogen is going to share a pair of electrons with one electron in water. So now each hydrogen has 2 electrons. Its shell, its one and only orbital full. Everything's good there for hydrogen. And on the other hand, oxygen is not sharing 2 pairs with each of the hydrogen, but it's sharing 1 of electrons with each of those hydrogens. The end result is the same, though. How many electrons are there in the outer shell of oxygen and water? Count them up, the little yellow dots. How many electrons do you see there in the outer shell of oxygen? Give you a hint right here in the camera, see? 8. So oxygen's content, right? So oxygen and hydrogen sticks together in a very set ratio, 2 hydrogens and an oxygen, and thank goodness it does this, right? We wouldn't have life on Earth if we didn't have water. We'll actually talk a lot more about water a little bit later on. We'll discuss it exactly. The entire chapter 3 is going to be discussing about water. Water, even though we take it for granted, even though, oh gosh, 3/4 of the universe, 3/4 of the universe, 3/4 of the planet, 3/4 of you is water, it's actually a very unique substance. Even though it's commonplace, it's very unique in its properties. Now methane. Methane is another example. Methane is carbon with 4 hydrogens. So carbon has the atomic number 6. All right, so how many valence electrons does carbon have? See if you remember what I mean by valence. How many valence electrons are there in carbon? That's the total number of electrons. And when I'm talking about valence electrons, I'm talking about those electrons in the valence shell. And the valence shell is the outer one. So how many electrons are there in the first shell? And then the difference is the number of electrons in the other shell. There you go. You got it. So 2 electrons in that first shell, in that one and only orbital. Carbon then has a 6 minus that 2. There's 4 left over. So there's 4 electrons in the outer shell. That means carbon is 4 electrons short of having a full outer shell. And so what it does in the case of methane is it shares 1 of each of those 4 electrons with the 1 electron that hydrogen brings in, and everybody's happy, right? Carbon now has 8 electrons in its outer shell. Each of those hydrogens has 2 electrons in their outer shell, and they're going to stick together. They're going to form a bond. Now, all along, I've been mentioning to you this idea of sharing electrons equally. I said, for example, in oxygen, the 2 pairs of electrons are going to be shared equally. They're going to whip around the nucleus of the atoms, and overall, they're going to spend half their time with the one on the left and half their time with the one on the right, and that's the same with the hydrogen. And in the case of methane, the electrons are going to be shared. They're going to be shared in equal proportions between the carbons and the hydrogen. So it's what we call an equal sharing of electrons. Equal sharing. Now, let me ask you something about sharing for a second. Do you have to share things equally? Is it a requirement to share things 50-50? No. No, of course not, right? I mean, I always use this analogy of a young parent driving around, you know, maybe doing some errands, and they've got 2 small kids in the back seat. And having had 2 small kids that were about 18 months apart, I have a lot of experience with this event I'm going to describe to you. So the kids are in the back seat, and you've been driving around for a while, and you know, they're getting irritated, and they're getting rambunctious, and they're fighting and doing the old "don't get on my side of the back seat" and all those things that kids do. You know, if you haven't had kids, you'll have the lovely experience of dealing with that when you do. And you have kids, well, then I'm preaching to the choir. You know exactly what I'm talking about. So let's decide that this parent just pulls over into a convenience store to get something to drink, and decides to go ahead and buy something for the kids to eat, so they'll have something to do. You know, buy them something to drink, buy them something to eat. So this parent, if they're not thinking, or perhaps they're a new parent, they might buy 1 bag of potato chips. All right. So they come back out to the car. Kids get into the car, and they put that bag of potato chip in the back seat, and they give it to the older sibling. And they say, all right, now you share with your younger brother or your younger sister. And the older sibling's like, okay, I'll share. So he opens up the bag of chips. Now, human nature being the way it is, and if you were the older sibling, you probably know where this is going. And if you're the younger sibling, you'll know where this is going. If you're the older sibling, are you going to share equally with that little brat brother or sister of yours? Are you going to make sure that for every chip you get, they get a chip? No. No, of course not. Now, you're going to share enough so that the little sibling doesn't raise a stink and then mom gets mad at you. But come on, you're going to handful of chips for me, a couple of chips to the little one. Yeah, maybe a chip, right, Logan? There you go. Just enough to keep them quiet. Now, again, back to my question, is that sharing? Yeah, it's sharing, but it's not equal sharing, is it? The same thing can happen with these electrons being shared between atoms. I mentioned to you hydrogen and oxygen and methane. Now, they share those electrons equally. As I mean by that, the electrons spend the same amount of time around both nuclei if we're talking about oxygen, or in the case of methane, we've got a total of 5 nuclei, the 4 hydrogens and the carbon. But those electrons are being shared equally, okay? In the case of water, though, and this actually has a lot to do with water's very unique property. I love talking about water because it's so commonplace, but when you get into it and you realize, water really is kind of strange. And actually, thank goodness that it is, for reasons that we'll talk about in Chapter 3. But what we say about oxygen is oxygen, the nucleus specifically of oxygen, has a very strong affinity for electrons. All right? It has a very strong, I don't know why I typed it twice, has a very strong affinity for electrons. What's affinity? What does that mean? If you have an affinity for something, what is it you have? Okay, yeah. You have a want, or you have a desire, or you have an attraction to it. There you go. Like you all might have an affinity for biology, right? Yeah. Or you might have an affinity for humanities, or you might have an affinity for water skiing, whatever. You may have an affinity for your friend or a loved one or a dog, right? You get the idea. Well, oxygen, now without giving them human characteristics, obviously they're not human, but the nuclei of atoms can have affinities for electrons. And some nuclei of certain atoms have a very strong affinity, and some have a much less affinity. Oxygen is one of those atoms that has a very strong affinity for electrons. As a matter of fact, we say oftentimes that oxygen is an electron pig. It loves electrons. Right? It has this very strong attraction, very strong affinity for electrons. So now oxygen, in my analogy, oxygen is the bigger brother or the bigger sister, the bigger sibling. It's going to share those electrons with each of those hydrogen atoms, right? But it's not going to share them equally. And so what I mean by that, and just to kind of use some rough numbers, and these numbers are probably nowhere near the exact values, but get the idea. So we're going to say that the electrons that are being shared between the oxygen and the hydrogen, they're going to spend, 70% of their time up here around the oxygen nucleus, and then the other 30% is going to be split between the 2 hydrogens. Now, don't focus on the numbers, folks. I doubt those numbers are anywhere near close, other than the fact that I'm demonstrating that the sharing is going to be leaning towards the side of the oxygen atom. So if you think of what that means that if we were able to look at a water molecule and follow the electrons around, we would notice that whenever we were looking for those electrons that are being shared with the hydrogens, they're going to be spending most of their time up here at this end of the molecule. Now, I changed words there for a second, right? The atoms are oxygen, hydrogen, carbon, all those things that are on the periodic chart, and a molecule is a collection of atoms. So what I'm saying in this case is the electrons that are being shared, see the arrows, the big blue arrows? that's indicating that the electrons that are being shared between oxygen and those two hydrogens are going to spend most of their time up at the top, up around where the oxygen atom is in the molecule. Now, this little squiggly gizmo thing indicates to you that what happens overall in the molecule, because the electrons are spending most of the time up at that end, that the molecule actually ends up developing a positive and negative ends, things that we call poles, positive and negative poles. Now, you may know poles as a structure, but batteries, a car battery has a positive and a negative pole. So that's another definition for it. So let me get my scribble here. So this water molecule ends up having positive parts of it down here where the hydrogens are, and a negative part up here where the oxygen atom is found. Now, the reason why we get this disparage of charge, this positive and negative, we can actually do the mathematics behind, or the arithmetic. Oxygen has the atomic number 8, 2 electrons in the first shell, 6 in the outer shell, right? That's how oxygen is sitting by itself. But when it's sharing a pair of electrons with hydrogen, that means many times, most of the time, in my example, what did I say, 70%? 70% of the time, you've got 8 protons in the nucleus of oxygen trying to balance out not 8 electrons, but it's 8 plus the 2 it's from each of those hydrogens. So you actually are going to have a situation where you've got 10 electrons spending most of their time surrounding the nucleus of oxygen, which has 8 protons. Now, we talked in class about the charges of those, and I wrote it on the board. I wrote it on the screen here. So if you've got 8 pluses, 8 positives, 8 protons, and 10 negatives, 10 electrons, that means, are you going to be net, right? And you know what net means. If you, not every single time, but overall, if you looked at a water molecule for a year, overall, would the oxygen end of the molecule be usually negatively charged, neutrally charged, or positively charged most of the time? What do you think? Yeah. Patrick, why do you say that? Why do you? What indicates to you that it's probably, what contributes to that overall negativity of that end of the molecule? What's that add up to? Yeah, right? That adds up to a negative value. Now, don't worry about the fact that it's -2. I don't care about the number as much. But what that adds up to, if you got more negatives than you have positives, then the overall net charge is going to be negative. Okay? Now, on the other hand, down here with the hydrogens, you've got 1 proton. Of course, it's positively charged. And most of the time, net-wise again, that end of the molecule is going to have a proton without an electron to balance it. Not all the time, but again, like what I say, 15%, huh? So in the obvious lot, or the reverse of that logic before, now we've got positives that have no negative to balance them out. So that means that down where the hydrogen atoms are, the water molecule is going to take on positive and negative charges. Or I'm sorry, yes, the water molecule, positive and negative charge. We call this kind of a molecule, we call this kind of a bond, if you will, a polar covalent bond. Polar covalent. It's sharing, but unequal sharing. And the result of the unequal sharing is the poles. Make sense? Contrast that with 2 hydrogen atoms. The electrons are being shared equally. The net difference in the charge is going to stay the same. You're not going to have positive and negative ends. So things like hydrogen, oxygen, and methane, they're polar, but they're considered non-polar covalent bonds. So we have two types of covalent bonds depending on whether you're sharing equally or you're sharing unequally. Now, that has a profound effect on how those molecules work together. And what I mean by how those molecules work together is, imagine a glass of water that's full of, I don't know, 1 billion water molecules. Each of those water molecules has a positive and a negative end. And just like the magnets you used when you were in school, what do positives and negative ends of something do? What do the positive and the negative ends of the magnets do? Yeah. So water molecules will attract one another. All right? They will actually bond. Not as strong a bond as the bonds we've been talking about, but they will form an attractive bond between them. Now, any more questions about covalent bonds? Because I'm going to jump into the next type, but it kind of segues in from what I've just been talking about. So we understand how covalent bonds work, right? In covalent bonds, you're sharing electrons. You can either do it equally, or in the case of water, you do it unequally. All right. Now, not the last, but the second bond I want to talk about is known as a hydrogen bond. It does not always involve hydrogen. It often involves hydrogen, but the type of bond that occurs is the bond that occurs between those water molecules, between polar covalently bonded molecules. All right, so let's make sure we're not confusing ourselves. Bonds can occur between atoms, and then also bonds can occur between molecules. In order for bonds to occur between molecules, those molecules have to have something that will attract one another. In the case of the atoms bonding together, it was trying to fill the outer shell. That's why they bonded. This is a little simpler. The reason why they stick together, the reason why those water molecules on the left-hand side, you see they're labeling, look, you got the negative end of that water molecule, and then the positive of that one. The reason why they're sticking together is just like I said with the magnets. They're electrostatically attracted to one another. Now, whereas we said that a covalent bond is indicated with a line, 1, 2, or 3. A hydrogen bond is indicated with dashed lines. So just so you recognize some of the symbology that's being used. So in the case what we have here is, was that 5? 1, 2, yeah, 5 water molecules. Those 5 water molecules are all attracted to one another. Now when we get into the next chapter, chapter 3, this is extremely important. This is crucial to life on Earth. Now it's real easy to break these hydrogen bonds. It's a lot more difficult to tear hydrogen and oxygen apart from one another, the atoms. But you can easily break hydrogen bonds. Very simply, pour yourself a glass of water, and when you get enough water and you tip the pitcher up, the water breaks. Yeah? So there's the water in the glass and water left in the pitcher, and what you essentially did is tipping the pitcher up is you actually separated those last couple of water molecules that were spilling over the edge of the pitcher. Very simple to break, right? You just tip the pitcher up, no big deal. Anybody can do it, even a child. So these bonds are the weak bonds, very weak, right? Covalent bonds, especially the triple ones, are pretty strong, but these are very weak bonds. But even though they're very weak, they are so important to life, folks. I can't really emphasize that enough. They're important to life on Earth because of what they do for water and the properties of water. And then later on in the semester, when we start talking about your genetic material, your DNA, much of it is held together by hydrogen bonds. So very weak, but very important bonds. Hydrogen bonds occur between water. Hydrogen bonds can occur between any molecule that has an atom in it that is an electron pig, that has an affinity for electrons. So in the case of ammonia, that atom is nitrogen. Nitrogen is similar to oxygen. It's going to share 3 pairs of electrons, one with each of those hydrogens, that's why it's NH3, but it's going to share them unequally. So that means, just like in the water, the end of the molecule that has the nitrogen atoms take on a net negative charge, and then of course we got the positive charge of the hydrogen, and those things are going to bond together. Now, this also talks to something about solubility. It talks to something about things that dissolve in each other. There's an old adage or an old phrase that I remember from my chemistry days, and maybe you guys do too: like dissolves like. So in other words, what we mean by that in the chemical sense is substances that are polar can be dissolved in other polar substances. For example, if you took ammonia and you poured it into water and mixed them, they would mix. Now, contrast that if you took water and, say, salad oil, vegetable oil, would those mix? Can you mix up salad oil? I mean, you can stir it, don't get me wrong, but if you let it sit for a few minutes, do they mix? No, The reason why is because while the water is polar, the oil is non-polar. So what you have is like the end of a magnet trying to stick it to, say, a piece of paper. Right? There's little, if any, electrostatic attraction in a piece of paper. So you're not going to allow, that magnet's not going to stick to it. If you take water and you get it close to other polar covalently bonded molecules, they will attract each other with hydrogen bonds. Now, that happens in ammonia. It also happens in these, down below we've got an organic molecule. Now, we'll talk about what an organic molecule is a little bit later on, but in a very simple sense at this point, organic molecules, among other things, would represent things like food. Right? Carbohydrates are organic molecules. So all of this is an organic molecule. And organic molecules, for the most part, always have an oxygen and a hydrogen in them somewhere. So here's that oxygen. It's attached to this molecule here, or this atom here, which is probably a carbon, and it's got its hydrogen. Now, it's not sharing that electron with that hydrogen equally. Now, so it's not like water. It's not got two hydrogens, but it's got that one. But the same result is going to happen. Because it's sharing those electrons unequally, that's going to be positively charged. All right, there's the negative charge. And so we can get a hydrogen bond between water and an organic molecule, specifically the oxygen and the hydrogen part of an organic molecule. Just as kind of a neat little fact here, if you eat a heavy carb meal, for example, folks always talk about having Chinese food. Chinese food is a lot of carbs, noodles, and those sorts of things. And the old funny thing about Chinese food is people say, you go have a Chinese dinner, and an hour later you're still hungry. The reason why that is when you eat a lot of carbs, it just doesn't have to be Chinese food, but when you eat a lot of carbs, carbohydrates will attract water molecules in your body. Okay, just like you see in the picture there. As you begin to digest those noodles, as you begin to digest that organic molecule, then those water molecules break the bonds. So when you first eat all the carbohydrates, you actually feel much fuller because those carbohydrates, those noodles in your body, are surrounded by water. Okay, it's like water. It's like grains of sand sticking to, like, say, a lollipop that you dropped at the beach. Those grains of sand would stick to that lollipop and surround it all over the place, making it slightly bigger, right? Minuscule, microns, but making it slightly bigger. So when you eat a heavy carb meal, the carbohydrates, because they're surrounded by what they call hydration shells. Not the same kind of shells in atoms, but basically a hydration shell is a layer of water molecules on the outside. And as that carbohydrate is broken down, those water molecules are removed, and the molecule's smaller now, and you feel full again. See, you feel hungry again because the organic molecule's gotten smaller. All right. Any questions on sharing of electrons, either sharing them equally or not sharing them equally? All right, so remember, there's a relationship between hydrogen bonds and covalent bonds. Hydrogen bonds result because of molecules, or excuse me, atoms that are sharing those electrons unequally. You can't have a polar covalent bond unless the electrons are being shared unequally. If they're being shared equally, then you won't get hydrogen bonds. Because if they're being shared equally, there's no positive and negative poles. It's kind of like sticking two pieces of paper together, right? Okay, the last one. Any questions on that before I get on to this last type? All right. The last type of bond is known as an ionic bond. And the reason why we call it an ionic bond is in chemistry, atoms that are charged are called ions. So what happens in an ionic bond is charged atoms stick together. Be very careful that you don't confuse that with hydrogen bonds. We talked about charges attracting things in hydrogen bonds. But in hydrogen bonds, it was molecules attracted to one another. Here in ionic bonds, we're going to talk about atoms being attracted to one another. A charged atom. You remember atoms coming out of the factory of atoms, if you will, have a neutral charge. Like, for example, sodium on the left. Sodium has the atomic number 11. Again, I'm not concerned with you memorizing atomic symbols or atomic numbers. Any kind of information like that you need for exams or assignments, I'm always going to give to you, or you can always ask me. But it's got the atomic number 11. So do some exercise with me. Sodium has the atomic number 11. How many electrons in its valence shell? How many electrons in its outermost shell? That's right. 2 in the first shell, 8 in the next shell. So 2 and 8 is 10. It's got 11, so you have to add one more shell, and it's got 1 electron. So sodium in the situation that you see in the picture on the left, this one right here, sodium has 11 protons, 11 electrons, and so 11 positives and 11 negatives, it's what we call neutrally charged, right? It has no charge. So it's not an ion. Chlorine, on the other hand, is the atomic number 17. And with the same argument, we can figure out that chlorine has 7 electrons in its valence shell. So sodium is missing 7 electrons from having a full shell. Chlorine is missing 1 electron from having a full shell. Now, there's a variety of ways this can be solved. Sodium could try to find 7 electrons elsewhere, and remember, it isn't a pool of rogue electrons out there wandering around. If there's an electron that you want to fill your outer shell, it's attached to another atom. So here's the situation. Sodium needs 7 more electrons. Chlorine needs 1 more. Sodium could either try to find 7 things to share electrons with, or, as you see in the red arrow, sodium could act as something we call an electron donor. See? Sodium and other atoms that have 1 or 2 electrons in those outer shells tend to be electron donors. That means they give up electrons, and on the other hand, if you give up an electron, something has to take it. I mean, we wouldn't have this discussion about bonds if sodium says, I need to get rid of that 1 extra electron so I have a full outer shell, and I'm just going to spit it off into space. It doesn't work that way. So if you have an electron donor, then chlorine has to be an electron acceptor. So in order to form an ionic bond, you have to have a donor and an acceptor. You have to have both. You have to have something that's willing to give up the electron. You have to have something that's willing to accept the electron. So we look at this situation here. Sodium and chlorine come together, and chlorine says, man, I need 1 more electron, and I have a full outer shell. Sodium says, wow, I think we're in business there, Mr. Chlorine. I've got 1 extra electron. And if I can get rid of that 1 extra electron, well, then that shell disappears. And the shell below that, it's full, which is what these atoms are trying to do. All right, very good. So let's do that. The red electron makes its way over here and begins whipping itself around the nucleus of the chlorine atom. All right, everything's fine, right? Look at the picture on the right. Cross the arrow. How many electrons in the valence shell of sodium? How many electrons in the valence shell of chlorine? Everybody's happy, aren't they? Sodium is happy. Chlorine is happy. I've got 8 electrons in my outer shell. All right, now, if you do the numbers, though, something has happened to those atoms. If sodium had 11 protons and 11 electrons, it now has 11 protons and 10 electrons. So kind of the same thing we did when we were looking at the water molecule. That means sodium is going to take on a net positive charge, right? And chlorine, in the reverse, had 17 protons, but it's now got 8 electrons. 17 pluses and 18 minuses is going to put you in the minus charge range. So those are two atoms are now charged, which is what makes them an ion. The sodium ion being positively charged and the chlorine ion being negatively charged. All right, now the terms that are in red, I want you to know those terms. A positively charged ion is called a cation, and a negatively charged ion is known as an anion. So sodium is a cation, chlorine is an anion. Now I know if you've had chemistry class, you've seen these terms a lot, because you talk about those a lot. This does not explain the bonding yet, though, or we haven't explained the bonding yet, and yet you can look at it and figure out what's going to happen. If this is positively charged, the sodium, and chlorine is negatively charged, what do positive and negatives do again? You sure do. So that means that a cation and an anion are going to stick together and form what we call a compound known as sodium chloride. So this is a salt crystal right here. The green ones are the chlorine and the sodiums are the yellow ones. So in an ionic bond, and this is, I say it only so to hopefully alleviating problems of confusion, an ionic bond involves positive and negative sticking together, as does a hydrogen bond. But in an ionic bond, what's positive and negative that are sticking together are atoms. In a hydrogen bond, what's positive and negative that are sticking together are molecules. Okay, makes sense? Any questions on that? Cool. So we have covalent bonds, electrons are shared. Covalent equals sharing. Hydrogen equals attraction between molecules. Ionic is attraction between, oh, it's spelled wrong, who cares, atoms. Now, one of the types of questions that I like to ask on exams, I'm very fond of compare and contrast questions. Compare and contrast questions ask you to do two things. They ask you to tell me the similarities and then also the differences. So on the exam, I might ask you to compare and contrast covalent bonds with ionic bonds with hydrogen bonds. So I'm going to want you to tell me what's the similarity between them and what's the differences between them. So if I'm studying my notes, one of the things I would add to my notes is a little table, and I would put compare as a column heading, contrast as a column heading. Down the rows, I would put the three types of bonds we just went through, covalent, hydrogen, and ionic, and I would fill in those blanks, what's the same and what's different between them. Okay? Need help on doing that, by all means get in touch with me, or we can talk about it in class. All right, now there is one other bond I want to mention, and only if nothing more for it's kind of what I call the ooh-ah factor. The ooh-ah factor is those things you learn about that you go, ooh, wow, that's really cool. So I throw this one in. It's a bond that's not real prevalent in biology, at least at the level we're going to talk about, but it doesn't mean that biological organisms don't use this bond. So let me introduce you to it, just one slide, rather briefly, only because it's just so doggone cool. This kind of bond is known as a van der Waals bond. It's a weak bond, and it comes about because of an asymmetry. All right, now, if you look at this picture right here, that'll help you with the asymmetry. All right, here's a simple atom on the left, a simple atom on the right. You got the protons in the middle, you got the electrons zipping around, everybody's balanced, everything is cool. That atom is neutrally charged. And I said that atoms out of the box come neutrally charged. You got 11 protons, you got 11 electrons. You got 8 protons, you got 8 electrons. But now those electrons, as I said, are zipping around the nucleus of those atoms. So now if you look down below where it says the simple atom, that means that sometimes, not very often, but sometimes you get a situation in which the atom on the left-hand side hello, hello, hello. Can you hear me? Yes? So, oh, I'm back. Okay. Where did I fall off? Don't worry about it. It was the previous slide. It happened after the previous slide. Okay, so van der Waals forces. Look at the two pictures that we got there. So oftentimes, most of the time when you look at an atom, it's going to look like the pictures up above. The electrons are, there you go, are scattered around that atom equally, and so that atom is going to be neutrally charged. But sometimes those electrons, because of the way they're whipping around, are just going to, by random chance, end up on one side of the molecule. One side of the atom. And if we have these two atoms side by side, and their arrangement is the way you see in the picture, where the electrons for the atom on the left are all on the right-hand side, and then the electrons for the atom on the right are all on the right-hand side, you get something that might remind you of a hydrogen bond. Now, this is not a hydrogen bond, but it's the same principle. Because you have all these negatively charged particles on one side of that atom, and all these positively charged protons, right? All these positively charged particles on that side, and if they're close enough to one another, 5 nanometers. Now, that's it takes 1,000 nanometers to make a micron. So we're talking a really, really narrow distance. If that happens, when they're that close to one another, there will be a slight attraction between them. Right? The negative electrons for the atom on the left will be attracted to the positive protons on the atom on the right for just a microsecond, because those electrons are zipping around, and so that bond that occurs is going to form and break within the blink of an eye. All right, now, as I said, we don't worry so much about those in most of the time when we talk about biology, but one of the things that helped answer these van der Waals forces, and this is why I put it here, is geckos. And there's a picture of a gecko there. Geckos, we have a gecko here in Florida. It's actually not a native gecko. It's a Mediterranean reef gecko. It came from the Mediterranean. A lot of stuff we get in Florida comes over on ornamental plants and stuff like that. That's why they happen. But geckos, and you can get on YouTube and look, I actually put a YouTube video in Blackboard for you guys to take a look at. Geckos can climb up vertical surfaces, even very slick vertical surfaces like glass. And you're thinking, you know, lizards can climb up vertical surfaces, but if you look very closely at that, lizards have claws, and even though they're very small, it's climbing, say, up your stucco. There's enough little nooks and crannies in stucco. It's kind of like climbing one of those climbing walls. They can get their little nails in there and climb up. So not really climbing up a completely slick surface. But glass is pretty doggone slick. So how does a gecko get up a glass surface? Well, if we looked at the toe pads of a gecko, that's what these are, and we magnify them with an electron microscope, we get something that looks like these bristles, right? At the very end, there are these very small hair-like, they're not really hair, but hair-like structures. And spread throughout one toe of a gecko, there are literally thousands or millions of these little hair-like structures, and then you spread that across all the toes on a foot and then 4 feet. What you get is just a boatload of these little bristle-like structures. Now, these little bristle-like structures at the very end of them have atoms, obviously. Everything is made up of atoms. And since there's so many of these little bristle-like structures, just in the order of tens and tens of millions, and of course, glass is made up of atoms, and the glass atoms are doing the same thing. Every once in a while, the electrons are on one side. Geckos are able to climb up slick surfaces like that because of the fact they take advantage of the van der Waals forces. Even though those van der Waals forces last for just a minute amount of time, you've got billions of places that's happening across those geckos' feet. So while maybe one of these little fibers sticks together for just a nanosecond and then comes apart, other fibers are sticking together. So a gecko plays kind of a probability game. It says, okay, so maybe atoms only form these van der Waals forces 1 in a million times, but if I have a bunch of places for that to happen, collectively, I can get enough electrostatic attraction. Even though each one is a very weak bond, I can get enough to help me stick to the glass wall, or to help me stick to the glass. Isn't that kind of neat? For many years, we didn't talk about van der Waals forces in biology because biologists used to say, well, van der Waals forces are something that happens in chemistry, but biological organisms don't use them. There is no examples of biological organisms using van der Waals. But when we look at the gecko, and of course, a lot of this has to do with technology and electron microscopes, we found out, no, they absolutely do. These little tiny bristle-like structures, the mass quantity of them allows this gecko to always have at least enough of them that are engaging in van der Waals attraction with the glass atoms to be able to climb up that wall. Isn't that neat? Geckos don't do very well on Teflon, though. Teflon atoms the molecular structure of Teflon is in such a way that you don't get real strong van der Waals. So they pretty much, they can get a little bit of attraction on them, but they certainly can't climb up a Teflon wall. Teflon is one of the slickest substances on Earth. I've heard it described as Teflon has the friction in Teflon is like if you took 2 pieces of wet ice and rubbed them together. That's pretty slippery, isn't it? All right, any questions on any of that? No. All right. I'm going to load chapter 3 now. We can get into that. Okay, anytime you're ready. Hold on a second, folks. Okay, one moment. Try it this way. There we go. All right. Stop. One little gremlin thing's creeping up. One more time. There we go. Okay, chapter 3. Water, 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 water. Water, water everywhere, but not a drop to drink. It's an old poem, isn't it? Samuel Taylor Coleridge, The Rime of the Ancient Mariner. Water, water everywhere, but not a drop to drink. The reason why is he's out at sea. Can't drink seawater, can you? 3/4 of the planet is water. Much of that is made up of the oceans. Seawater will kill you if you drink it. It dehydrates you. It also causes neurological imbalances. So if you're ever out on a cruise ship, or you ever have a shipwreck out at sea and you're stuck in a raft, don't drink seawater. But we do need water for life. And water, even though seawater you can't drink, it's still important for life as well. What is it about water? What is it about water and its properties of water that makes it so unique and makes it so crucial for life? Well, let's take a look at that. Water molecules, you remember, form hydrogen bonds, right? That's what we just talked about. Now, those hydrogen bonds are very weak attractions between those water molecules. As I said, you can easily break a hydrogen bond by just simply tipping a pitcher up when you're pouring water. But I mentioned that even though they're very weak, they're so doggone important. Now, chemists will tell you that if you look at the molecular properties or the physical properties of a water molecule, and you compare it to other molecules that are not water, but are similar in terms of structure and weight and all that sort of stuff, that water, based on the temperatures, the average temperature on Earth, water on Earth should actually exist mostly as a gas. Yeah? Three states of matter, right? The solid, the liquid, and the gas. So what they're telling us is, based on just kind of looking at it on paper, if you were comparing water molecules to other similar type molecules, the water on Earth should all be gaseous water, or most of it should be, and it's not. Most of the water on Earth, there is gaseous water, right? There's water vapor, steam, and of course there is solid water, that's ice, but most of the water on Earth is liquid water. And life as we know it, and this is what's very exciting about astrobiologists finding life on other planets, life as we know it needs liquid water to survive. Well, if you remember back from some of your early science classes, you might know that solid, liquid, and gas has something to do with density. Solids have greater densities than liquids, and liquids have greater densities than gas, right? What we mean by density, we did the calculations in class the other day, density is mass divided by volume. Right, so what we're basically saying, density is the concentration of atoms in a set volume. Let's say a milliliter, or a liter, or 8 cubic centimeters. That's a volume. If you have a lot of atoms in that volume, you have a lot of mass, and that tends to be solids. If you have very few mass in that volume, very few atoms, that tends to be a gas, and in between are liquids. So what you do when you boil water, right, is you heat water up, and water molecules actually can absorb a lot of heat. It's the whole thing that you put water into a microwave. It takes forever to boil the doggone stuff, doesn't it? These hydrogen bonds between the water molecules, in many cases, kind of act like springs. And they spring back and forth as these water molecules are being heated up. All right? Once you heat them up enough, the springs actually break, and the water molecules, the hydrogen bonds, separate, and these water molecules separate, get further away from each other, less density, and it becomes a gas. When you cool off water, the water molecules get closer together until they form ice. All right, so there is a relationship between these hydrogen bonds and the fact that water stays a liquid on Earth. Remember, the chemists are telling us that based on just looking at it on face value, water should be a gas. But what is not being factored into that, and chemists know this, I'm not saying they don't know this, is the fact that water molecules are polar covalently bonded molecules, and they stick together. These slight hydrogen bonds prevent these water molecules from going off by themselves and becoming a gas. They attract them together and keep them as a liquid. All right? So that's very unique about water. Water tends to stay a liquid when, if you look at it on paper, it really ought to be a gas. All right, so properties of water. All of these properties of water have so much to do with hydrogen bonds. For example, water molecules stick together. Number one, they have cohesion. And I've showed you that that works. Now, from a biological point of view, why is that important? Well, let's take a look at a picture and see. Look at that tree on the left-hand side. Okay? Water rains down. Water rains down onto the ground, gets into the roots, and then water somehow defies the laws of gravity and ends up moving up a tree tens of feet, hundreds of feet, because the water is necessary in the leaves of the tree. Water is also lost through trees as well. It's a process that's similar to sweating in us. It's called evapotranspiration. So that's what this is showing you, that water actually evaporates. Now, what that helps do is keep the tree cool, of course. But how do the water molecules get up the tree? How do they defy the laws of gravity? Well, water molecules are moved up a tree through little tubes, water-conducting cells that make tubes. So on the left-hand side, you see the tubes, so we're moving up this way. And since those water molecules are polar covalently bonded, because they have those hydrogen bonds, because they have that slight attraction, they not only stick to each other, but they stick to the walls of the tubes. So what is happening at the very top, where the water molecule is entering, say, the leaf, to be used in photosynthesis, it's like these water molecules are actually slightly attached to one another. So as this water molecule gets pulled up the tree, it is slightly attracted to the water molecule behind it. And so like train cars, it gets pulled behind it. and that pulls the next one, and that pulls the next one. That goes all the way down to the tree, and somewhere out there in a root, there's a water molecule that's just outside the root, and there's a water molecule inside the root, and as this one gets pulled up the root, because all of these are being pulled, it pulls the water molecule into the root. Now, this slight adhesion that you see between the water molecules and the sides of the tubes would not happen if it weren't for the hydrogen bonding or for the polar covalently bonded water molecules. Think about lab we did the other day. What did we do in lab, or what part of lab did we work with that physically demonstrated this idea that water molecules will stick to the side of a tube like that? Do you remember the part in lab and I was describing to you what it looks like and how important it is to read this particular instrument? I'll get rid of my scribble while you guys are thinking about that. What did we do in lab the other day that could physically show you that water molecules are attracted to the sides of a tube? Perfect. Thank you, Jessica. Yeah, remember the graduated cylinders? Yep. Yeah, that's fine enough. Yeah, in the graduated cylinders, remember I said in the especially thinner ones, the graduated cylinders tend to make a meniscus. That upward turn in the edges is because the water molecules are being attracted to the glass. So it's pulling them up. It's called capillary attraction. Capillary attraction. Okay. Now, if you take my Bio 2 class, we'll actually look at the anatomy or the internal structure of plants, and this is a cross section through the stem of a plant, and these are all the tubes I'm talking about. All of these are tubes that carry water and nutrients up and down the tree. Even really kind of cool, look at the spider walking along the surface of the water. See, a lot of insects, water striders, for example, and organisms that you may have seen, can walk across the surface of the water. Why don't they fall through? Well, number one, they don't weigh very much. And since they don't weigh very much, when they force down on the surface of the water, now this wouldn't happen to you. You step off of a dock underwater, you're going to go right to the bottom because of your weight. Yeah, you got it, Amber. There's surface tension. Isn't it cool? Look at that picture. Look at the picture of the spider's legs. It's pushing against the water. Notice how the water is dented? You see that? The reason why the water is dented is because the weight of that spider is flexing, or it's stressing those water molecules. It's causing those hydrogen bonds to be under tension. Now, they don't break, because if they break, the spider goes to the bottom. But it's just enough attraction to allow this organism to walk along the surface of the water. Very important for those critters that do that. Okay, now you can actually kind of demonstrate this at home. If you very carefully, you can actually float a dime on the surface of water. And it's the same thing. You very gently lower that dime and very careful with it. That dime will float on the surface. Again, little weight, just enough to kind of indent the water, not enough to break all the way through. All right, let me go back to this because, yeah, paper clips will do it too. That's right. It's got to be light. You couldn't put a brick and do that. The next two things I want to talk about have to do with water and heat. It's called the high specific heat of water, and the fact that water also has something called a high heat of vaporization. I lump those two things together under temperature moderation. Now, the reason why you see the seesaw again is, if you remember, temperature moderation is one of the things we talked about when we were discussing entropy in living things. If you can't maintain the proper temperature, then entropy increases. If you can't cool off when you sweat, then, right, bad things happen to you. So water has this high specific heat and this property of the high heat of vaporization, and that ties directly in to this ability for living organisms to use water to maintain this temperature balance. I'm running out of time to actually get into it, and I don't want to fly through, so I'm going to go ahead and end class right there today. We will get back on this next Wednesday. Remember, we don't have class on Monday because it's Labor Day. But we will have a lecture again online on Wednesday. All right? So if there are no further questions, you guys have a good weekend. Try to stay dry. And as by all means, please start working on those assignments. All right, I'm going to stop the recording.